Hello everybody, welcome to this new Cambridge Spark webinar. I'm Raoul, and today I'm going to talk about making sense of big data file formats. So this is definitely a buzzword compliant webinar, great for fancy dinner parties as always. So file formats sounds a little bit interesting, isn't it? So unfortunately I can't see you all here. But I'm sure if I ask you, have you ever heard about CSV files? A lot of you would raise their hands in the air. They are everywhere. We can't escape from CSV files. And if I ask you, have you heard about JSON? Well, that's another file format that's really common on the web for serializing and deserializing data. Now, some of you might come from a more enterprise development background, maybe in Java, and I'm really sorry if I'm bringing back bad memories, but XML is another example of a file format. So just to provide some motivation on what are big data file formats, I think it would be useful to just talk about traditional file formats such as CSV, JSON, and XML. So for the purpose of this presentation, what I've got here is a few files. So we've got this lone CSV file, and we also have this open library JSON file. So if I look up a little bit what this CSV file is all about, you can see it's not pretty. It's not pretty at all. We've got a bunch of columns here separated up by commas, and then we've got the data. Now, CSV is not really a sophisticated file format. For example, it doesn't support a list of values for a specific column. Now, JSON is slightly more sophisticated because it supports things like dictionaries, where you can say, here's a value given a key, and also supports lists. So those are really common file formats that you will work with as a data scientist. Now, what can we do with those? Well, let's take a look at a little notebook here. And what I've got here is two files, so lone CSV, which is around 400 megabytes of data, and this open library JSON file is around about 100 megabytes. Now, what's really useful with those file formats is that they provide a standard way to represent the data, which enables multiple applications to load the data and process it. So for example, here I'm making use of pandas to read this CSV file and then say, well, just show me the first kind of 3 rows. So we got a standard representation for this data. Now I can find out what its shape is, how many rows, how many columns. I can do some processing. So for example, here I'm saying, well, describe me the column funded amount, because we've got loans, and give me some statistical information. Now pandas will deal with all of that by loading the CSV file and transforming it into a common object. Now we can do something really similar with JSON. So here I'm going to say, well, let's use pandas again to load up this JSON file where each line in a file is a JSON record. Load this up into a pandas object, so a data frame, and then print out the first 3 rows. So this seems like it's all fine and good. So what's the real problem? Well, let's go big data. We've got some files here that only have a couple of 100 megabytes. What if we had gigabyte of data? What can we do? Well, clearly my little laptop here will not be good enough. So what we're going to try and do is to distribute the work over a cluster. So for my demo, to motivate the need for big data file formats, I'm going to have a big JSON file. It's about 92 gigabyte of data. And that is stored on S3. So S3 is a service provided by AWS, which lets me store data on the cloud. The next thing I'm going to do is to set up a cluster of machines where I can distribute the processing of this big data file. So what I've done here is to set up a cluster with 16 machines. So they're called N3X large. Sounds really sexy. And what it really is, it's essentially a machine that has around 16 gigabyte of RAM and a quad-core CPU. So we're going to use all those machines here to process a big data file. So I've set up a notebook using Zeppelin, and that's again provided by AWS. It provides you a notebook to interact with your cluster of machines. And what I'm going to say here with this little query is say, well, first of all, load up this big JSON file, and then parse each of those entries as a string to JSON. So we're going to get Python objects after those strings are parsed. And then find me all the books that have Cambridge in the title. So Cambridge Spark, we are based in UK, in Cambridge, where our office is. So I'd like to find out how many books there are where Cambridge is in the title. So if I run this query, and if you're wondering what is special code here, it's using something called Spark, which is a distributed processing framework. And I run this query, suddenly it's going to be executed on my cluster of machines. You know, they're going to have to coordinate their work here to find out the result. So, as you can see already, it is pretty slow. The job has started, and you know, we don't really have time to wait so long. Just imagine on one computer, but now we're using 16 machines, and it's still really slow to find out the result for this query. And that's the purpose of this webinar. Can we come up with better tools and better representation of that data to reduce the latency of this query? So let's go back to our slide and try to understand what the problem is. So here is some data taken from a presentation from Jeff Dean back in 2009. So Jeff Dean is a little bit like the god of distributed systems. He's a fellow engineer at Google. And in 2009, he showed this data in one of his presentations. And what that shows is that a cache reference is really cheap. It's just like 0.5 nanoseconds to look up some data from the level 1 cache. Now, if we go to the main memory, suddenly this becomes really expensive. We have 100 nanoseconds. Now, the exact numbers here have to be taken with a grain of salt. We obviously are in 2017 now, but the ratio between those different speeds is what really matters. It's more expensive to go to memory than it is to look up data in the cache. Now, if we go to the disk, so maybe an SSD, then it's even more expensive. Suddenly, here we're talking about milliseconds. Now, if we go to an old style of a hard disk, then it's even more expensive. Now, if we go over the network, so just sending a packet from California to the Netherlands and back costs 150 milliseconds. And that's the real problem. When we talk about big data, and when we have a cluster of machines that are processing information, they will have to load the data from the disk. So that's going to be really slow. They will then need to load this data in the memory and then in the cache. And in order to be able to coordinate their work, they're going to have to exchange data over the network, which is even more expensive. So that's the problem with big data, is that there's a lot of data transfer, a lot of data load, and we're paying a high cost for that. Now, the other problem is that CPU and memory speeds have evolved at very different ratio over the last decades. So if you look at this graph, you can see that since the 80s, memory speed has steadily increased, right? So we've got a 10x improvement over the last couple of decades. Now, CPU and the processor speed have increased at a much larger rate. So it shows that there's a bit of trade-off. We would be way better getting a CPU to do a lot more work because it's cheaper, whereas memory is slower and doesn't evolve at the same speed. So this is where big data file formats comes in. It's a realization that in order to get more speed and to reduce the latency, we're going to have to be making use of a CPU more, and we're going to have to make better use of how much data we're working with. If we can reduce the amount of data that we're working with, we reduce the I/O, and we decrease the latency. So the questions are, well, what kind of layout can we come up with that optimized common query? And what kind of layout can we come up with that makes storage more efficient in order to reduce how much I/O is required? And that's what big data file formats comes in. Now, just to take a step back, let's look at this really simple example. I've got some tabular data that represents loans. So here we have a row that has a loan ID. the interest rate, how much we're going to loan, and then what's the term for that loan. So 36 months. Now the question is, given this data, how do we represent it so we're able to store it to disk? And when we mean representing data, it means we need a translation mechanism that converts this data into bytes, because ultimately that's what is stored on the disk. So what are possible approaches? Well, the first one is a very simple row layout. It's the idea that we take each row, we append them one after the other one, and that's what we write to disk. Now, a query like select all from loans where ID equals 0 is going to execute really fast because of a property called spatial locality. And that's the general idea that data that is available next to each other is a lot cheaper to load and process. For example, in SSD, we load a whole row of data. And what that means is that a whole sequence of bytes will actually be loaded in memory. So if the data that we want to query is available readily, one after the other one, that's very cheap. We only needed to do one load. Now, in terms of memory, this data will be loaded in the cache. Cache have a fixed cache line, and again, that will load a fixed amount of bytes that are available one after the other one. So it's really cheap to load and process data that has a special locality property. Now, if we take a different approach, maybe a column layout approach, so what that means is that instead of having each row appended one after the other one, we're going to take the values for each column. So for example, here, all the IDs, and then append the values for the next column. So all the values for the interest rate, and then the values for the amount, and finally the terms. Now, a query like select all from loans where ID equals 2 is going to suck, because suddenly we don't have all the values available next to each other's. We're losing this spatial locality property. We're going to have to do multiple references and multiple lookups. And as you saw in my previous slide, that comes with a cost, especially if we have to load it from disk. So sad emoji. I know there's a few emoji fans here, so here's a very sad emoji. Now, let's come up with another query. What if we want to do something a little bit more realistic, something that a data scientist would need to perform to provide some insights back to management? For example, how much did we actually lend in a given period? So I want to say, select the sum of the amount from my loans. Well, suddenly the row layout becomes the bad student, right? Because all those values are not accessible one after the other one. So we're not making use of this spatial locality property. We're going to need multiple disk lookup and memory references. Our cache will not contain all the data, so we're going to get some cache misses. This data has to be loaded, so suddenly we're paying a high cost. However, the column layout is really going to shine. Suddenly, all those values here, all the amounts, are readily available one after the other one. It'd be loaded in one lookup, and it becomes really cheap. So the column layout really shines for this kind of query here, where you want to say, well, I just want all the values for one specific column, because they're all available one after the other one. So let's just take a step back here and really understand the pros and cons for those two representation approaches. The row layout approach means that the records are stored sequentially one after the other one. And it's really good for the kind of queries where you want all the data for one record. Now, the column layout means that all the values for a specific column will be stored sequentially. And it makes it really efficient to access a subset of those properties. So for example, saying, I just want the amounts, or I just want the term and conditions. And there's another benefit that because homogeneous data is stored one after the other one, that means compressing those values will be a lot better. So think about a timestamp, for example. If we got a sequence of timestamps stored one after the other one, we could potentially encode those using a delta, which would be a lot more efficient in comparison. So column layout really shine when we've got this kind of more business intelligent or analytical queries where you need to query a subset of those columns. So where do big data file format comes in? Well, a big data file format sounds really fancy, but all it is a specification for how to represent data, and that sits on top of a file system, for example, the Hadoop file system. We'd like it to be language independent. So what that means is we should be able to work with this file format from Python, from Java, from Scala, from different libraries. It should be specified independent. It would have a binary representation, which means it would be encoded into bytes, which are then stored on the disk. And ideally, it's supported by common execution engines. So if you're familiar with Spark, we'd like to be able to use this distributed processing framework, or maybe Hive, Impala, and other kind of big data databases. So what kind of big data file formats have we got at the moment? Well, you may have heard of a few, including Avro, Parquet, and ORC. Now, Avro, honestly, doesn't sound really sexy. Avro, and what it is, it's a layout that represents data using rows. So rows will be appended one after the other one. So it's really suitable for those kind of queries where you want all the information from a specific record. Now, Avro is not just a file format specification. It also comes with a whole RPC library. So it's really designed for doing serialization and deserialization over a stream of data, or maybe communicating with different web services. Parquet, however, sounds really cool. A nice little French tone to it, Parquet. And what it is, it's a column layout, so really suited for queries that involve a subset of the columns. And it's also able to store metadata within the file specification. I'm going to come back to this topic, but what that enables is really optimization of different queries. And Parquet came up from Twitter a few years ago, and it's also now maintained by Cloudera. There's another file format called ORC, which stands for Optimized Raw Columnar Data, and it's also a column layout, and it supports a built-in index, different statistical information that are stored as part of the file. Now, what I want to do in this presentation is to focus on Parquet. And Parquet enables different querying optimization. In particular, two optimization, one called predicate pushdown and the other one called projection pushdown. Again, really fancy, really awesome for those fancy dinner parties where you have to wear your tux and your boss is sitting next to you. You cannot tell him, hey, we're using Parquet. It's got predicate pushdown, and your boss is going to be, wow, I need to give this person a raise because it sounds really smart. But let's try and shed a bit of light on what that really means. So if we take a look at this query here, select name and state from a table of customers where the ID is greater than 10,000 and where the ID is smaller than 40,000. Well, what predicate pushdown really enables is to say if there is some metadata stored in the file that tells us that a group of rows has a minimum and a maximum ID, that potentially we can use that information to decide whether we need to scan each of those rows. So if a group of rows says that actually the minimum ID is 50,000, we know that we don't need to scan this group of rows because obviously there's not going to be any rows between 10,000 and 40,000 as an ID. That's impossible because the minimum is 50,000. So this is how we can skip some scans of the data. So that's really useful. Now, the other property is called projection pushdown. And that's the idea that we only need to read the columns that are actually required. So in this query here, we're saying just select the name and the state. So only those columns will need to be loaded from disk to memory and then in the cache. We don't need to load any other information. So that enables you to reduce how much data is loaded and also how much CPU time is used to process the data. So that was one part of the story. We now have a layout that optimizes querying. Now, the other side of the story is, can we come up with a more storage efficient way to store this data? And Parquet has a few encoding tricks to reduce the size of the data that needs to be loaded and processed. In particular, I've highlighted a few of them. So dictionary encoding, run left encoding, delta encoding, and bit packing. Again, Sounds really fancy. Let's take a look at the notebook to see what each of those encoding really means. So I've written some code ahead that's going to help us understand what each of those encoding is. So the first one, dictionary encoding, is the idea that if you got some data, so here represent a column, so a few names in the team, so Raoul, Olivia, Thibault, Lucy, Patrick, and Tim, their favorite programming languages, so obviously Python is everyone's favorite language when you're a data scientist, and the different postcode where we are living. Now, dictionary coding is the idea that if you got a lot of repeated data, you could replace that data with a symbol that has a length that is smaller. And that means you're able to compact the data. So the first thing that's required is to generate different tokens to represent repeated symbols. So for example, CB1 is repeated 3 times. We've assigned it the symbol 3, which is cheaper to represent. Python, we've assigned that the symbol 7. Now what we can do with that is to encode the data using those generated symbols. So we can go from this to just this representation here. And visually, you can see that it's a lot more efficient to represent that through symbols. It's cheaper. Now, you will never need to implement dictionary encoding yourself. Parquet supports this encoding for you. Now, another encoding is called run length encoding. And that's the idea that sometimes you've got repeated data. So for example here, let's pretend we have a list of IDs that we'd like to be able to encode. We've got 555, 0, 2222, 25. Clearly, there's a lot of repeated information. So by encoding it, we can say that actually the number 5 is repeated 4 times. The number 0 is repeated once. The number 2 is repeated 5 times. And finally, the number 5 is repeated once. So what we're able to do is, again, to reduce the size of the data. We can go from this to something that's more compact. And we will let the CPU unravel the data to decode it. Because if you remember, CPU is a lot cheaper than loading data. So that's the real trick that we're making use of. Now, another encoding is called bit packing. That's the idea that some numbers are really cheaper to represent when they're smaller. So if you take the number 1, you know, on my 64-bit architecture here, representing the number 1 requires 64 bits. That's crazy. Think about all those bits that you could use to represent other data. So bit packing says, well, you don't need 64 bits, you actually need something smaller. So in this case here, I'm gonna pack the number 1 by only using 5 bits. And visually, again, you can see it's a lot cheaper to represent. Now, the wins, the gains, are become even more relevant when you've got a list of data. So let's say we've got a list of IDs here. I want to bit pack them. If we use the traditional approach here where we're not doing any encoding, you can see we're paying a high cost. There's a ton of bits here that we're not using, all those zeros. Now, if we bit pack this list using 5 bits to represent each number, you can see the sequence is a lot smaller. So again, less data to load, less data to transfer. Let's use the CPU to decode it, which is more efficient. Now, finally, another encoding that Parquet uses is called delta encoding. So let's say we've got a list of timestamp here to represent maybe some log data on different events that customers have interacted with on your website. What we can do here is to say, well, hold on, those timestamps, clearly there is a sequence, there is an order. We went from something that's in 68, we've incremented by 1, then we incremented this by 2. And what delta encoding is going to do is to say, well, take the first timestamp in the list and just add the delta 1, 2, 4, 6. And when you need the real data, let's just get the CPU to calculate the sequence again. What that enables you to do again is to have a more efficient way to represent that data. So Parquet supports all of that out of the box. And again, that makes the data more efficient to store. Now, this sounds really great, but how do we actually work with Parquet? Well, there's an interesting project that is fairly recent called the Avro Apache project. And what it is, it's an in-memory columnar database. And that really bridges the gap between a file format and the memory representation of that data. So Parquet represents the data in a file, and Avro will take that data and represent it in a memory efficient way so that different architecture can make use of the data. So here I'm using the PyAvro project, which is a Python port of the Avro project. And what we're going to say here is load the loans here. So if you remember, there was a pandas data frame. And what we're going to do is to store this panda data frame here into a Parquet file. So we're using the Avro project to do this. And now if I want to read this file back, what we can see here is that we're able to read it, and we're able to get a pandas data frame, and then finally we get the different columns and rows. Now what's the win? Well, let's list the file, and we can see a new frame here, loan Parquet. What you can immediately see is that it's already more efficient to store in comparison to this kind of good old CSV file. It's about twice smaller. So that's already handy, and we're able to load it within pandas. Now, we could go one step further. So encoding is quite cheap to do. We could decide that actually we want to use a more sophisticated compression mechanism. So maybe I want to take that data, gzip it, and store it as a Parquet representation. Now, this little piece of code here, using, again, the PyAvro project, we'll take the data, compress it, and then store it into this Parquet file called loan-compressed Parquet. Now, you can already see it's a bit slower because it's a more expensive compression mechanism. But if I now look at the different files that are generated, we'll see the loan-compressed file that is now 71 megabytes. So we're starting to get the benefits here, because if you think about big data, where storing large quantity of data in the cloud can become really expensive, we're now making that cheaper. Now, that sounds all good and nice, but how do we go from data that is stored locally to data that is actually on the cloud? What I want to do now is to demonstrate how we could work with our file that was 92 gigabytes of data to its Parquet representation. So what I did for the purpose of this demo is to take the file and write it to a Parquet representation. So let's get the size of this file. What we can see is that it's now 11 gigabytes. So we went from 92 gigabytes to 11 gigabytes just by writing it as a Parquet representation. Now this is a huge win. That means we're able to reduce the cost of storing our data by using a big data file format. But what about querying this data? So let's go back to our cluster of machines here that is running. And what we can see is that the query that I ran earlier here using the JSON representation took 3 minutes and 45 seconds. That's a long time. Now, what I'm going to do now is to run this query again, but using the Parquet representation of my file. So what we're saying here is use Spark, and it supports Parquet out of the box. And we're saying, well, load this Parquet file from this S3 source. That will be available as a data frame that has some schema that it's learned from the Parquet representation. We're saying filter all those entries where the title contained Cambridge, and then finally count it. And what you can see is that now that took 30 seconds. This is a huge speed up, right? We went from around 3 minutes and 45 seconds to 30 seconds, just by using an alternative representation. So what's the moral of the story here is that, well, not only are we getting a reduction of the file size, which enables you to save cost, especially if you're storing this data in the cloud, but you also getting a current speed up. And this is really important as a data scientist, is that suddenly you're able to interactively process a large quantity of data, something that wasn't possible if you were using something like JSON or CSV. So a few further notes on this talk. So if you're interested in different benchmarks for comparing Avro, Parquet, and ORC, there's a few empirical studies that you can look at. So the first link here. Another one by AWS that looks at how do we build a big data storage solution, and it shows how to convert data with around 1 terabyte of information to use Parquet using the AWS services. So I quite encourage you to look at this white paper. It's really interesting. There's a few potential features that will be added to Parquet. The first one is Bloom filters. And what it really would enable, so if Bloom filters were stored as metadata in a Parquet file, that means membership access would become really cheap. So there's potentially a feature here that will come in a future version of Parquet, and also a way to enable a different library to add custom metadata that can be used to make querying more efficient. So to conclude, it's not just about JSON and CSV. There are big data file formats that are really suitable for processing and storing large quantity of information. And a big data file format like Parquet improves querying speed and makes storage more efficient. So it comes with really two great benefits. And on top of that, Parquet is already supported by popular execution engines that you may be using, such as Spark, Hive, and Impala. So I hope you enjoyed this webinar. For those of you who are not familiar with Cambridge Spark, we provide professional development for data scientists and developers. In particular, we run a 6-month part-time bootcamp delivered in London. So if you're interested in becoming a fully qualified data scientist working on industry-relevant problems, we've got a course running in London with a cohort starting in February. We've also recently launched the online version of this course. So if you're living in other parts than London, this course is available, so do get in touch. And finally, we are also running a conference in Manchester where we've invited different speakers that are going to share how they make use of data science in practice. So we have a fantastic set of speakers, so do check this out. And if you're interested to have a training course for your own employees and your own team, we deliver different courses. We would come to your office, so different courses in data science, in Python, in machine learning, in big data. So check it out. Do get in touch with us. And it's been a real pleasure to deliver this webinar to all of you. If you have any question, do get in touch via our website. I'm always keen to hear feedback and how we can help you. So thanks for listening, and see you at the next webinar.